Right now, the next 2 units are going to involve the discussion of this particular document. It is the March exam, and I would like you all to have a copy of that in front of you. Now, if you haven't, will you pause this video and will you print it, please? It's an attachment. It was sent out to you already, so you have the use of it if you want it to be useful. I'm holding the scripts. We'll be returning them to you in due course, but I am just saying to you we need to go through the content to make sure all the bits and bobs now are sorted out. Now, because I've gone back on some material with you on the mole and masses, gases and moles, and we've gone into stoichiometry, this should now be an entirely different document. This was set by Sarah, and I'm going through it with you now, okay? But I'm going to tell you it should now be a document that you have got. I could really do that. I think I'd score much higher now. I hope you'll be thinking like that we've tightened up on a lot of things, because I think it will be, we're going on to a new section when this paper is finished, okay? So it's important that we get through it. So that's the document you want, okay? And you have a total of 4 pages in it, yeah? You have a total of 4 pages that you need to work on to go through that. So I'm going to go through them with you, and it's going to be all board work now, please. I have left the periodic table there. I'm just reminding you all, we have to look up relative atomic masses every now and again for things that are going on here. Question 1 on this paper gave you a diagram with a burette and a conical flask. And it asked you various questions about a procedure that is on the syllabus. It is, in fact, washing soda, right? They didn't necessarily mention that, but that's what it's about. It's about a hydrated sample of sodium carbonate. I'm going to read the question first, and then we'll go through a structured answer for that. In an experiment, 4.69 grams of hydrated sodium carbonate, Na2CO3.XH2O, were weighed out and dissolved in deionized water. The solution was then made up to 250 centimeters cubed in a volumetric flask. I can't guarantee you that they would always say in a volumetric flask. When you hear 250 centimeters cubed, it would have to be a volumetric flask. Okay, good. 20 centimeters cubed of this solution was transferred to a conical flask. If you're transferring it to a conical flask, it has to be a pipette. Okay, keep that in mind. Okay, and titrated against the standard 0.13 molar hydrochloric acid solution using a suitable indicator. Now, I'd like to think that you were ready for this, that you would be in a position to animate that. I'm going to do it for you now. Now, the animation, I really believe in this. I can see all the accurate candidates scoring high because it takes some time to prepare the answer. Every question you get in the insert will be different. It will be a different slant on the same topic. So you need to make sure you have noted all these pieces, okay? So many grams of this were weighed out. I'll put it in a beaker again for you, okay? A heap of this stuff, and it happened to be 4.69 grams. 4.69 grams of hydrated sodium carbonate, Na2CO3 dot, and they've written in here XH2O. Now, I wonder, do I need to say anything to you about that? When you have sodium carbonate with H2O after it, that's called water of crystallization. So that is a crystal, because that's its water of crystallization. All crystals have water of crystallization in them, and they are part of the molecular structure. The number of waters can vary. They have an X in here for the moment, so part of your task will be to find the value for X. But at this stage, I'd like you to just realise that. If that was missing altogether, then that would be known as anhydrous sodium carbonate. Anhydrous meaning without water. It would be a powder. It would not be a crystal. Okay, but this is the crystalline substance. That is effectively washing soda in everyday life, okay, is what you're dealing with there. The solution was made up to 250 centimeters cubed. So they weighed that out on the scales, obviously. You would then add some water to it to dissolve it, and it was then made up to 250 centimeters, okay? 250 centimeters in, obviously, in this case, in a volumetric flask. Now, that obviously is that, and then this went in here. And they'll ask you all the issues about that in due course. But that's it. It was made up to 250 in a volumetric flask. 20 centimeters cubed of this solution was transferred to a conical flask. One conical flask coming up. And so there is 20 centimeters cubed. Now hold a moment, please. What would you write here? You would write Na2CO3 question mark. You don't know how much of the 4.69 grams is sodium carbonate and how much is water. You don't know. So you now have a sodium carbonate solution whose concentration is not known. If there was no water there, then it would be that many grams per 250. So you could have that many grams per litre. You could really quickly work out its concentration. But because there's water involved in the mass, and we don't know how much, then of course we don't know the concentration of this. And likewise here, Na2, CO3, question mark. I'm looking for its concentration. Is that okay, everybody? And that's what I told you there. Okay, it was transferred to a conical flask and titrated against the standard HCl solution. I'm drawing my burette here, okay, and that's HCl, and it's a standard solution, so they give you the concentration 0.13 molar. You know its concentration, all right? Using a suitable indicator. We'll come to this in a moment now, but that's very important for us to transfer to a conical flask, okay, and it was titrated against a standard hydrochloric acid solution. Now, they ask you various questions for to continue with the detail here, so I have to work my way through that. Part A, describe the procedure for dissolving the hydrated salt and making up the solution to 250 centimeters cubed. Describe this. Okay, now I've dealt with that already, but very briefly, let me remind you again, please. You drop names. You use as many bits of equipment as you can. You weigh this in a clean, dry beaker on a scale, so top pan balance would be fine. And you would say you zero the top pan balance and you transfer the solid to it using a spatula until it read 4.69, until the scales read 4.69. Zero the scales with the beaker on it, or use a clock glass. The clock glass can be a bit messy. I find it easier in labs just to use a beaker, a clean, dry beaker, tell them that, put it on the scales and zero the scales. Using a spatula, scoop this solid in here until it reads 4.69. Very good. Now, take this from the scales and add deionized water to it and stir it with a glass rod until it is completely dissolved. Until it is completely dissolved. Are you okay with that? Now, wash a volumetric flask with deionized water only. Rinse it with deionized water to clean it. Now, using a funnel, pour the contents of this beaker in here, wash the beaker several times, and transfer all the washings to the volumetric flask. Okay, so you wash it several times. The whole purpose of the exercise is to make sure that every last grain of the 4.69 grams ended up inside the volumetric flask. Now, that's very, very important, that all of that ends up with it. You must give the examiner the impression that that's the case, right? Now, you do that using a funnel. I've mentioned in the last unit. You never put anything into this flask without putting a funnel in there because it's a very narrow neck. Okay, now when you're 1 centimeter from the graduated mark, remove the funnel and bring the level of the liquid up to the volumetric graduation, that mark there on the neck. Bring it up to there using a dropper or using a wash bottle. A wash bottle will do fine until the bottom of the meniscus corresponds to that, right? The bottom of the meniscus corresponds to that. Now, stopper and you invert and you shake it. You shake it every time before you use it to get a homogeneous mixture, to get it evenly mixed, okay? Now, that's very important. Now, that was one. They could have asked you anything else. How did you transfer it after that? They didn't ask you that here. How did you run the titration? Now, be ready for all of those, please. It's very important, but that was the bit there. They've asked you to describe that, okay? Next, part B. There was, by the way, 15 marks for describing that, and most candidates would only get 9. Now, please, I'm trying to taunt you a bit here to realise that detail is left out. The more bits of apparatus you mention, the better, right? Beaker, top hand balance, okay, spatula, deionized water from a wash bottle, stir with a glass rod, funnel, okay, pour through the funnel, remove the funnel, dropping bottle or dropping pipette, and put in the last few liquids, stopper and shake. The more bits of apparatus you name, the more likely you are to get the marks. Name a suitable indicator for the titration and state the colour change observed in the conical flask at the end point. Now, an indicator for this now. I have touched on this with you in class. I demonstrated the 3 indicators. There are only 3 indicators in acid-base titrations. Now, I could be showing you them, but I don't think I'm doing anything to help you at this stage. There's another part of your course that would explain that to you. I had this up earlier today. Maybe I'll just show it to you again to give you a sense of where that is. Every one of these has a suitable indicator, and there are the 3 indicators that you need, right? We're using sodium carbonate and HCl, so methyl orange is the indicator. If you're using hydrochloric acid and sodium hydroxide, you want litmus. And if you were using hydrochloric acid and washing soda, methyl orange, again you can see, and vinegar, you need phenolphthalein. There are 3 of them there: methyl orange, litmus, and phenolphthalein. Now, I'm not going to give you an explanation here because there's a whole section in chemistry that does that. Okay? Methyl orange, litmus, and phenolphthalein, and just put pH down there. Right? That is used for a titration with involving a strong acid and a weak base. Litmus is used for a strong acid and a strong base, and phenolphthalein is used for a weak acid and a strong base. Now, there's a whole section on your course on weak and strong acids. I'd rather wait until you did that to deal with this. I think I told you in class to just memorize this, that I'd expect you to know that the indicator here was methyl orange. Okay, I think I'd expect you to know. There's only 3 of them there, by the way. Look, methyl orange in 2 of them, and litmus and phenolphthalein in the others. And that's all you would need to know, and that would be rather important that you follow that up, okay? So will you take it, please, that, whereas you might say, I didn't know that now, or I would be sure that, I understand that. But all these questions are set in Leaving Cert based on the premise that you have the full syllabus covered. Okay, so at this point in time, I'm acknowledging you don't have the reason behind this. It asks you clearly there, okay? It asks you to name a suitable indicator for the titration. Methyl orange will get you 3 marks. State the colour change at the end point. The 2 colours for methyl orange. I demonstrated this to you now, so you saw me doing this. If you put methyl orange into a base, it's going to remain orange or yellow. And when you add acid to it, it will turn red or pink. Pink is a dilute red, okay? That kind of thing, right? So, and that's exactly it. It's going to go from yellow to pink, or it's going to go from orange to red. Now, I don't like you using the word orange because you'll be accused of taking out the name, if you know what I mean. Okay, so it's a dilute version of it, so yellow to pink. The first permanent pink colour would mean that you've used up all of this. Okay, that's what it would mean, and that's what they wanted there. State the colour change then, it is yellow to red or yellow to pink. Okay? Explain why not more than 1 or 2 drops of indicator should be used. And again, that's part of that section you have yet to do. You won't do it until later on in the syllabus, so you have to be aware of that. And the answer is very simple. Indicators are always either weak acids or weak bases. And if you put too much of it into this flask, you're going to interfere with the titration, which is an acid-base titration. It's going to give you an incorrect result. Okay, they're either a weak acid or weak base, and therefore they would interfere with the titration. It's only 1 or 2 drops. I think you remember when I demonstrated, I cheated a little. I put extra indicator in there so you could all see the colour. But you shouldn't do that. The slightest amount, if you're standing over it, that would be very important. And you'd be, that's most important that you're aware of that. Right. Now, after carrying out a number of accurate titrations using a 20 centimetre cube, using the 20 centimetre cube sodium carbonate solution, the mean titration figure was found to be 20.17. 20.17 came out to be the titration. Okay, that's the mean titration, 20.17 of the 0.13 molar hydrochloric acid. And that they've given you that now at last. We had this complete and you can work on it, and so we're ready to go. It says the titration reaction is, and I better write that out for you so that you are in a position to use it. I'm writing it out on top of the board. You wouldn't be doing this in the exam now, okay? Na2CO3 plus HCl goes to, and they gave you the 3 pieces, sodium chloride, carbon dioxide and water. Okay, they gave you all of these, all right? And there's a balancing number there of 2. It's a balancing number. Now that's given to you, remember, will you please? And the only function that serves for you is there and there, all right? Very important. Calculate the concentration of the sodium carbonate solution in moles per litre and in grams per litre. Now, that wasn't very difficult, it was straightforward enough, but you have to have your information. Now, I'm saying again to you, that's a great help, that you know what's going on there, okay? That's very, very important. I'm going to do that with you then. M1 V1 over N1, M2 V2 over N2. I hope you can see that. M1 V1 and M2 V2, okay? And now we need to put a tag on that for you. That's the sodium carbonate. Na2CO3 is the tag. and the HCl is here. Okay, now I'm recommending the tag to you. You mix up your numbers always. Okay, M1 you're looking for the concentration of sodium carbonate. The volume of sodium carbonate is right there. It's 20. That's quite unusual, by the way, to have a 20 centimeter cube pipette. It's very likely at your level in secondary schools that we'd all be using 25. But it's the even number is the thing you know. And you knew it went down here, so that had to be the pipette, okay? And the ratio of sodium carbonate to that's a 1. Look, 1 to 2. 1 to 2. You get that from the equation. That's the number of moles reacting, and there you have it. Equals the concentration of the HCl is there, 0.13 multiplied by the volume. The volume is 20.17, and you're dividing by 2. Right? 2 for that, and so you must solve for M1. And I solved for M1, and it came out to be 0.0655. 0.655. That is it. And now, do you know you're on the road map? Here I go again. Your moles per litre, I should have written that as molar or moles per litre, and I should have tagged it, okay? Na2CO3, very important. Okay, so that's that, 0.0, something like 0.066 maybe there. I think I would even go maybe 3 decimal places, all right, that's fine. And grams per litre then, you must multiply by AMR. So to be that multiplied by, I think that's 106. 2 sodiums, 23 is 46, carbon is 12, and 48. 10, 16, that's right. 106 is the MR for that, which you get from your periodic table, okay? You get from your periodic table, that's fine. There's no issue with that, that's fine. And that equals, multiplied by that, and I got a value of 6.99. Did I did it? 6.99. 6.996 I got grams per litre Na2CO3. Na2CO3, okay? I have a number, I have a unit, and I have a tag. Now please, there are the 2 answers, and there was 9 marks for that. Now folks, every time you do this, I'd like to think you do that as well. Now remember, they'll ask you about procedure, so you kind of visualize the procedure when you do that doodling. I'd strongly recommend it to you when you're doing any question like that. I think you're likely to get all the marks out of the question if you do that. Okay, we're not finished. There's another part of this question. And the part of the question now is calculate the weight, it says in your paper. I prefer the word mass, mind you. The weight of water in the original sample. Now, that's called water of crystallization. They didn't say that in the exam, so just be careful of that, just in terms of what you're actually doing there, okay? Okay, that's water of crystallization, right, in the original sample, and hence the percentage water of crystallization there. Okay, so now as a result of this, we have to make up a further chart for ourselves, okay? We know the original mass, that includes all of this. Let me just mark it out for you. That includes 4.69 includes that. Now, we are now only talking about sodium carbonate here. So if I have moles per litre, grams per litre, if I could now get grams per flask, I would be very close to what I need, okay? That's grams, so I'm dividing that, and that's where I'm going to get it up, right? That you work your way through that, okay? And that's what you have there, more than anything else, okay? That's going to give you grams per flask. You're to divide by 4. That's going to be divided by 4, 1.75, I've rounded it off to 7, okay, grams per 250 centimeters cubed. 250 folks, there, 250 centimeters cubed, okay, of sodium carbonate. Now, I've just calculated, are you okay? I've just calculated the mass of that out of the whole lot. And thankfully, that is smaller, that many grams is smaller than obviously the 4.6, and that's what we have to do. Now here's what I'm going to do next. They've asked me specifically to calculate, to make sure I just right, calculate the mass of water in the original sample. The mass of water in the original sample. So here's how we do that, okay? I'll write this and see if it's okay. Mass of Na2CO3.XH2O equals 4.69 grams. Now, you can see over there, that's that. Now, as a result of the titration, I have mass of Na2CO3 only, that's the sodium carbonate, and that is 1.75. So by subtraction, I can get the mass of the water of crystallization equals. Are you okay with that? A simple subtraction. And this came out for me to be, what have I got for you? Yeah, it came out to be 2.94 grams. Okay, very important now. Now, I believe that we did one of these already with impurity, and I bet that could just as easily be an impure solid, and that would be the impurity. So you get the mass of the whole lot first day, including the water, and then as a result of the titration, you get the mass of only the active ingredient, which is the sodium carbonate, and as a result of that, by subtraction, you've got the mass of that. Now, I'd like to think that that table would be used by you. Biggest problem I find here with candidates is they cut corners. Quite good at the subject, but they start doing calculations. This has nothing to do with maths, everything to do with your chemistry. Lay it out like that, look, and you'll have no problem. They're all grams, okay? And by subtraction, I got the mass of the water crystallization. They've asked me for that, and that is an answer in itself, okay? That is an answer in itself. I'm reading what they asked you. Calculate the mass of water in the original sample, and hence the percentage water crystallization in the hydrated salt. Now, the percentage water is fine, then that's easy enough, isn't it? The percentage of anything, let me do that for you. The percentage water of crystallization is the mass of the water of crystallization over the mass of the crystal, that's the whole lot in other words, multiplied by 100. And that's equal to, mass of water crystallization is 2.94. The mass of the original crystal is back up here, 4.69 multiplied by 100. And that gave me an answer of 62.6%. 62.6%. And there's your answer. Okay, the mass of the water crystallization over the mass of the whole lot by 100. That I've told you already, that's a statistical measurement. There would be no issue with it at all. Okay, what is the percentage boys in a class? It is the total number of boys over the total number including boys. The total number including the water crystallization by 100, and therefore you have that. And that's the one you want for that. There's no issue with that. That's that part of it. Finally, and they regularly ask this when this comes up, they want you to get the value for x there. Okay, to get the value for x. Now, I need space on my board here, so I'm going to scrub this piece. Am I okay? Are you all right with that? If I scrub that, you don't need any further knowledge on that there, I don't think. We can deal with that, okay? So that's what I'm going to do with you now. I'm going to get rid of this piece here. Right? Good. You want to get the value for x, okay? Getting the value for x. Now, I've introduced you to a method in stoichiometry now, and here it comes alive for you. Very useful. Anytime you're asked to get x in that, make ratios. Now, that's my cliche, okay? Make ratios. Make ratios, okay? This is the technique I'm talking about. Ratio number 1. Now, it doesn't matter what the ratio is, as long as the two of them are the same. And I'm going to put XH2O on top, and I'm going to put Na2CO3 below. Okay? So this is the theoretical ratio. So it's going to be 18x. Do you know where I got that from? You got that from your periodic table. Oh, sorry, maybe I should have left my periodic table up here for you all the time, and there would be something at least that you know. You have that in your own book now, please. You can go and look for that. Please do. Okay? Go and look for that because you need it. Okay? But look, in the exam, they'll all be given on the front. They will all be given on the. They'll be given on the front of your exam paper. Okay? And rounded off. Okay? 16 and 2 is 18. Are you okay with that? And this one here we worked out already is 106. So that's one ratio. And the second ratio now, this is a method, by the way, making ratios. Second ratio, it's the same, it must be the same, H2O over Na2CO3. That's called the theoretical ratio because you didn't need any exam question for it. It's just the theory of it, okay? It's what you've worked them out to be. This is the practical ratio based on the experimental results which are here. What's the mass of water crystallization? There it is there. 2.94 grams. Now, what's the mass of sodium carbonate? There it is there, 1.75. Now you're finished. Put that equal to that and solve for x. Okay, that's all. 18x all over 106 equals 2.94 all over 1.75, and go and solve for x. Okay, go and solve for x. And I got 9.89. 9.89. Okay, 9.89. Now you might say, how would you get 0.89? You realize that's an average. We can explain that quite easily. How would we explain it? Some of these crystals would have 10 water molecules in them, and some would have 9. And the average comes out to be 9.89. Now that's the full question, and that would have been worth a further 6 marks. Now, like the idea here that some parts are difficult and some parts are easy, we must confront that. If you have a method, then that doesn't arise. You developed a technique. Here's how I do this. Now, I hope you're taking something on board here, that you're changing something. I've been appealing to you now for a few weeks to do that. Lay out what's happening. Every year it is different, okay? That's down here, that's up here. Would that always be the case? Probably. But you have to be sure. The numbers will be different, okay? And just be careful as to how you go about that. There's an expectation that you will get that right, and that's very good. Now, that is one question fully complete. And what I'm going to do is I'm going to do the second question with you now, and we'll leave 2 questions in the first unit, and we'll do the 3 questions in the second unit is the best way to do this. All right? So that's the end of volumetric analysis. Before I leave it now, let me just remind you there are only 4 possible titrations in acid-base titrations. Only 4. Now there's 4 more in redox. In our next session, I will be doing oxidation and reduction, as I've reminded you already. And we have to do all the oxidation and reduction section before any volumetric could be done in that. Okay? And it is important that you would have oxidation and reduction done very well. We have acids and bases done quite a while before we ever went into volumetric. So I'd like to think that you know that we'll have this wrapped up now and concentrate only on the acid base now, please, and get them right. Okay? It's very important that you will be able to handle that and that you'll be clear no matter what they give you, you'll have a working method for it. I hope that that will be the case. All right. I'm going to look at the second experiment then. The second question on your exam paper is also a mandatory practical. By the way, these are mandatory practicals, and it's very important that you will be attending to them and that you will make sure you have a record of them. The second one, I've discussed in class with you already, and I've discussed in a previous video, so you should be fairly good at this one. In question 2 reads, in an experiment to determine the relative molecular mass of a volatile liquid, a sample of the liquid is vaporized at a given temperature and pressure, and its volume measured. The mass of the sample is also measured. And they proceed now to ask you various things about this. The number of moles of liquid is then calculated using the formula PV equals nRT, and from this the relative molecular mass of the liquid is calculated. There are 2 terms underlined in that. One is volatile liquid and the other is relative molecular mass, and they ask you to explain the underlying terms. So, can you explain volatile liquid? A volatile liquid is a liquid with a low boiling point, and therefore it easily vaporizes. Okay, it has a low boiling point, so it easily vaporizes. You weren't asked any more than that now, that would be fine. But I want to just tell you there's a piece of chemistry that would explain that to you if you were asked to explain it. You weren't asked here now, but if you were. Why is something volatile? Because the intermolecular bonds are weak. There's nothing holding the molecules together, so they fly off into the air. And that's what you need. And you have to revise that section. I think I've told you several times already. Van der Waals, dipole, and hydrogen bonding, very important. You weren't asked that here now, just what is a volatile liquid. And secondly, you're asked to define relative molecular mass. You have to tell me it's the average mass, it's molecular mass now, right, of the molecules of an element or compound. Remember, elements put of molecules or compounds put of molecules, okay? And they are compared with an agreed unit. And the agreed unit is on a scale where carbon 12 has a mass of 12, or compared with 1/12 of the mass of the carbon 12 isotope. Okay? And they're 2 4s, easy marks, you know, and you should really be sharp on that. Now, they ask you all the following then, right? Explain the terms of the first one for 8 marks. Now, describe with the aid of a label diagram how you would carry out this experiment in a school laboratory. From your description, it should be clear how the mass, the volume, and temperature of the sample are measured. Now, folks, can I just pause for a minute there and say to you, that's mandatory. And because it's mandatory, of course, there's an expectation that you're very familiar with it, okay? That you've seen it done, or you've done it, okay? And that's vitally important. And I'm going to do that for you now. It asks you specifically to describe with the aid of a label diagram. I'm going to draw the diagram for you. Will you be careful with it, please, now that you get this right, okay? Now, I'll warn you about various things in a moment. You take a flask, and you have basically a conical flask inside it. I've shown you this already now, and here I'm drawing this now. You see, I'm drawing this just like you, okay, in the exam, and I'm saying to you, I've no ruler. I'm not worried too much about the quality of my diagram, as long as everything would be labelled, and that's the way it should be with you. You immerse this flask eventually in water, okay, very important, and you have a heater underneath here. Okay, you have the volatile liquid in there, right, and that's boiling water, okay, which I mentioned a moment. You would need to show some kind of support here. This is a retort stand, and that is a clamp to hold it. Do you realise an empty flask will not remain submerged in water, it will float. So you have to make sure it is submerged, that is practically totally submerged in the water. So tell me there's a clamp there. Put a thermometer in here, please, for respectability, will you? And label it, okay? You label that, you label that. You label this, of course, yeah? You tell me that that's water, right? Will everybody be careful, please, with the level of the water? Will everybody be careful? It's a very common mistake for people to have the water down here. Okay, that's terrible. The entire flask should be practically immersed in a temperature of 100 degrees. So it's very important that you wouldn't make that mistake. Now that's even casual look, okay? It should be up there, as high as you possibly can, and the clamp is keeping it submerged. There's a pinhole there which you must label. That is tin foil and a rubber band. You need to label them, okay? Now you put all your labels way out here over the way, everything is laid up like that. But label everything. Assume the reader of your script has no chemistry. Is a very good approach. Don't be so mad, they know what I mean. They may well know what I mean, they won't give you the marks, okay? They can only judge you what you write. Label everything, okay? Level of the water so the flask is practically submerged. Tell me there's a pinhole in the tin foil there. Tell me that's tin foil. Have a heater underneath it. Have a thermometer in the water. You can tell me the water is boiling. I'm okay with that, okay? Throw a few bubbles in there for a laugh, okay? And tell me the water is boiling. Now label everything. Okay, and that, by the way, should be 1/3 of an A4 page. One A4 page, 1/3 of a turn. Okay, like too many people are drawing diagrams carrying a lot of marks that are way too small. Now, we'll describe briefly what you have to do here. I'm reading the question again now. Describe with the aid of a label diagram how you would carry out this experiment. And here's what you'd be saying then, please, I'll give you some idea. You would take a conical flask and attach tin foil to the top of it, held in position by a rubber band, and you put a tiny pinhole in that tin foil. Okay? Before starting the experiment, put some volatile liquid in there. They recommend propanone to you, by the way. That's mentioned on the syllabus, propanone. We'll come back up in a moment, an organic compound. I would have picked that. It has a low boiling point, so it will vaporize very easily, right? In there, okay? That's what you do. And listen to me now, you basically have to describe clearly what you're going to do. You weigh the flask and its attachments before you start the experiment. The flask, the tin foil, the rubber band with the pinhole in it, empty, you weigh first. Then you put some volatile liquid into it and you set it up in the apparatus as shown in the diagram. You say that, set it up as shown. Use your diagram to your advantage, right? You proceed to heat the flask as shown in the diagram until the last drop of liquid disappears. And when that happens, you have a flask full of vapor. You have a flask full of vapor. When that happens, you have a flask full of vapor. At that moment, the moment that the last drop of liquid is no longer visible there, remove the flask from the water. When you remove it from the water, its temperature will rise, will drop, of course, because it was in boiling water, it is now in the room. And you'll find that the vapor in here will condense. Take it out, and it will condense. Leave it sit there for a few minutes, you'll see all the liquid, you'll see all the gas condensing to liquid. Dry the outside of the flask when it has cooled down. Dry it thoroughly when it has cooled down, and weigh it again. And the difference between the mass of the empty flask at the beginning and the flask full of vapour will give you the mass of the vapour. Okay, now they ask you a very direct question here for you, so you should have to work on this. They have a very direct question. The question asks you in the course of, okay, how you will carry out the experiment in a school laboratory. From your description, it should be clear how the mass, the volume, the temperature of the sample were measured. The mass was got by weighing the flask at the beginning when it was empty, putting some liquid in there and placing it in the apparatus as shown, and heating it until all that liquid disappears. You now have a flask full of vapour. You now remove the flask from the water, leave it cool down, dry the outside and weigh it again. And basically the difference in the two masses is the flask full of vapour that you wanted. That's the mass. That will carry the most marks. Okay? The volume is got at the end of the experiment by taking the conical flask when you're finished, remove everything from it, fill it with water to overflowing. Fill it to overflowing and pour the contents of the flask into a graduated cylinder and read the volume. And lastly, they want to know the temperature. The temperature of the vapour is got by having a thermometer in the boiling water throughout the experiment. I think most of us don't use that in practice. We won't tell anybody, but we don't use it. Okay? We know boiling water is close to 100, but you take that. It might come out at 99 now, that's neither here nor there, but show a thermometer there so you've shown intent, and that would be very good. Okay, very good, that's that, and there was 21 marks for all of that description. How may the pressure be measured? You make a comment on the pinhole that if there wasn't a pinhole in the tin foil, that the pressure of the vapour inside would blow the cap off the flask. That didn't happen. Consequently, the pressure inside must equal the pressure outside. In other words, any extra vapour would be able to escape. So the pressure inside equal to pressure outside. The pressure outside is atmospheric pressure, so you go to the nearest barometer, and the barometer is going to give you a reading of today's atmospheric pressure. And that pressure, the atmospheric pressure, is equal to the pressure of the vapour, so you get it from a barometer. Okay, very good. And lastly, I think they have, that was a separate 3 marks. And lastly, they have the calculation. Now, the calculation, of course, is something we have to be careful with, and they have given us all the details we want. I think we're okay with that. I'm going to list the data for you. The temperature is given to you at 97 degrees Celsius. Okay, the pressure, the volume is given at 132 centimeters cubed. The pressure is given to you at 1 by 10 to the power of 5 pascals. And R, the universal gas constant, is available to you at 8.331, and N you're looking for. Now, how are you fixed, guys? Do you know what you're doing? Units are the big thing here. You know about the formula, don't you? PV equals nRT is given to you. The minute you see that formula, you're thinking metric. That's metric, so everything must be metric. So you must convert that to, was that 273 to that? Okay, and that's what you're doing, 273, and you're going to get, out of that, you're going to get 370 Kelvin. 370 Kelvin, yeah, 273 for that. 273, okay, that's what you're at there, right, and that's fine. Next one, that's centimeters cubed. Do you know you must convert it to meters cubed? And do you know how to do that? Now, it seems a silly unit, I said at the time of doing this, please be careful. The error rate here now is shocking. It is terrible. There's no excuse for it, okay? Just you have to be aware. That has to be metric, but you like it or not, that's fine. Okay? And that's pascals, you're okay with that already. That's already good, and that's okay. And so you go and solve for N. Okay? I'll say the more to you. N equals PV over RT. Put in your 4 figures. Please don't just give me an answer to that now. Put in the numbers, evaluate the 2 of them and show me that. Evaluate 2 of these and show me that. And then divide that by that. Don't just turn up a number, will you please? The error rate here is quite high. And you're going to get N is equal to, I got N equal to 0.0043 moles. 0.043 moles, okay? And now there was 12 marks for that. There was 12 marks for that. And can you see yourself losing marks all over the place if you're not aware of the method and the units there? That's very important. And lastly, part E, calculate the relative molecular mass. You know how to do that, don't you? 0.0043 moles has a mass of, and they gave you that in the question, has a mass of 0.25 grams. So 1 mole has a mass of X grams, and you go and solve for that. And I got 58.14. 58.14 grams. That's the MR. That's the MR. Now, I've been through this already. I'm not making a big deal because we have it done already. So I'm expecting you to be aware of what's going on there. I hope that's okay. Can I remind you, please, I have the name written down there. You probably haven't it done yet, but propanone has a formula, CH3COCH3. And if you do a quick touch on that, 3 carbons are 3, that's 36. 1 oxygen is 16. And 6 hydrogens is 6 hydrogens is 6. That's 8. That's 58. Okay, so like you are, it is that. Okay, now it could be a lot of other things as well. It doesn't have to be propanone. Propanone is fine. Why did I pick propanone? It has a boiling point of about 55 degrees. If you take the lid off an acetone or propanone bottle, I think I mentioned to you already, you get a sharp vapor from it. You shouldn't inhale it, by the way, but you get a sharp vapor from it because it vaporizes easily. It's a boiling point in the 50s. So in a warm room, it will start to volatilize, and that'll be very good. Now, there are 2 fairly calculating questions on this paper, and I just break the unit for you now because you might want to go back and revise them, and with the next unit we'll complete the paper, all right? Good.